Okay, so there's a couple of things that I want to look at today. One of them is that I want to implement immediates, but the other one is specifically relating to the scaled index work that I did. So if we look at, for example, this multiply by 1 and multiply by 2 scaled index here, NASM optimizes these to just be RCX and RCX plus RCX. So these give the same behavior, but they result in a shorter instruction encoding. So what I've done actually works for this, but I didn't test yet these special case registers, and I didn't test extended registers. So SP is not available as a scaled index register, so I can skip that and just go straight to R12, then do RBP, and then do R13. So if I just regenerate this listing here, go to the tests and add those. So those are here. So we'll change this to R12. This one will be BP, and this one will be R13. And then if I run this test here, we can see that there's some problems. So I'm missing the SIB here. I'm missing the displacements here, 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 and here. And then the rex prefix for the extended registers is incorrect. So luckily this is an easy fix. The problem is that I'm doing the transformation for the optimization after I output the rex prefix. So moving this, this can be an if, up to before I do the rex prefix will make sure that the rm variable is actually finalized by the time that I'm doing it, and then it means that it can output the correct bits. And actually looking at this, the D function already ignores explicit zero displacement, so if I just take this and unconditionally do the displacement here, and I'll put this in the outer scope because I know that I've got this down here, so I can just get rid of both of those, there and there. Now that this has been moved out before the rex prefix, I can move this into the outer scope. So if I do a test now, now we can see that the rex prefixes are all correct, but I'm still missing the SIB and the displacement for the special cases. And that's because when I rebuild this operand here, I'm throwing away some information. So I'm always assuming that the flag is just reg, but really these special cases have memSP and membp in them. So to fix this, I'll do some general purpose registers array. Put the general purpose registers in the array. And then I can use the index registers index to look up the original operand from that array. And then that will make sure that I've got all of these special flags on there that are required. So if I do a test, that now passes. So now I can move on to implementing immediates. So let's do some tests here. So we'll do a MOV into CL, which will be like -1, and we'll do OX80 maybe, or maybe 7F and FF. We'll do the high bytes as well. Then we'll move on to 16 bits. So this will be CX. We'll keep one of these byte operands around. And then for each time we move up a size, we'll keep the lower sizes, at least one of them. And then we've got 64 bits. Okay, and then we've got memory destinations as well. So I'll get rid of these CH ones. These can all just become a memory access on RCX. These ones will be bytes. this will be word. Then we've got dword. And then we've got qword. But qword, I think with the memory destination, it doesn't support 64-bit immediate, so we'll get rid of those. Let's just see if NASM complains, so that's all okay. Then I just need to move these into the tests. So we'll go to the encoder tests, put all of these in. So these will be MOV with some size, and then we've got CX, some immediate, NA, NA. And so the size is first. So this is bytes, and actually these bottom four are going to be CH because those are the special case high bytes. These ones are going to be word. This one is dword. This one down here is qword. Then we've got bytes, word, and dword, and then finally qword. Okay, so now the way that I thought that I would implement immediates is that these have to be operands still. So I'll just have another constructor function called I, which I pass the immediate into. Let's just get all of these. Okay, so we'll go to get the immediates and then put them all into this I function. Okay. Right, so let's just regenerate the NASM and do the go test. Yeah, okay, I've got to implement the I constructor. So func I is going to give an operand, and we're going to return operand where the info is the fact that it's an immediate, and the value is just the uint64 of the immediate that's passed in. So this will be immediate, which I'll say is int64. And now Go is complaining because I've got these numbers that overflow. Unfortunately, I don't think I've ever actually been helped by this message, but so we'll say overflow, let's say 8 and F or something. And if I define them up here as overflow 8 and F as a uint64, then the conversion should make the Go compiler happy. Okay, so overflow, undefined overflow F. Oh, I've misspelled it. Okay, need the immediate flag. Immediate. Okay, so we can't match any forms, which is normal. So looking at the MOV encoding table here, so this is the MOV one. Down at the bottom, we have all of the immediate forms. So there's 8-bit, 16-bit, 32-bit, 64-bit, 8, 16, 32, 32. These are M1s only accept up to 32. And in the case where it's a 64-bit destination, you still have the rex W here, but it's sign extended. So this actually gets used for some instruction length optimizations. There's also some different notations going on here. We've got +R something, and we've got /0. So until now, we've just been doing /R, which is the mod RM, reg, and RM are used to do the operands. In the case of these other notations, if we just go up to the chapter that actually describes them, So digit is basically saying that there's a digit between 0 and 7, and it indicates that the mod rm byte uses only the rm field, and the reg field actually contains the digit that they say. So if it's /0, then it means that your mod rm is whatever your mod is. Then you have to put the 0 in there, so this would be 0 as the reg, and then the rm is the only field that's actually still used according to the operand that you want to select. If this was /1, for example, then you would set the reg to 1. If it was 2, you would set it to 2, etc., etc. The slash or the plus R1 is saying that the lower 3 bits of the opcode itself are used to encode the register, and that the mod rm byte is actually omitted entirely. So for example, one of the opcodes in the MOV was B8. This had this plus whatever notation here. So if you wanted to select the register CX, that is the index value for that is 1, so you would OR that with 1 to give you B9 as the actual opcode. So this is the opcode, and it's the register selection at the same time. And actually, while we're here, if we look at the rex prefixes, or actually a bit down from the rex prefixes, there is an immediate section. This says that in 64-bit mode, the support for 64-bit immediates is accomplished by expanding the semantics of the existing MOV reg im16 and 32 instructions. So if the opcode is between B8 and BF, then it means that the 64-bit immediate is supported. So this is basically the MOV into a register supports 64-bit immediates. So back to the MOV encoding pages, if we just define some forms for all of these things. So first we've got the MOV to a register from an immediate. So we do immediate here, we don't need the mem anymore. The bytes one for this is B0 and the other ones are B8. And then in this case we've got the plus RB, so this actually means that there's no mod RM, which I've already got a flag for. But we also need to tell it that the reg is in the opcode now. So we'll need a new flag for that. So we've got reg in opcode. And then we need a couple more forms. So this is where it can go into RM. So this is reg or memory. And this is C6 and C7. So C6 is the byte one and C7 is the other one. These ones are just opcode extensions with the digit. So actually these will need a new field, which I'll call opcode-ext, and we'll pass in like opcode-extension 0, for example. So this will be a new form field, opcode-ext. And the way that I would like to do this one is that if I use 0, or if I just use a byte, that's a bit difficult to it's a bit awkward to encode into the forms and stuff, because 0 is also a valid extension. So instead what I want to do is have this type opcode-ext, which is a struct that says whether it's valid or not, and then if it is valid, then we use the byte. So we'll just define these. We know that there's 0 to whatever, 0 to 7, so we got 0, shifted up by 3, because this has to be ORed in with the mod rm byte as the reg field. And then we'll just make sure that we've got 0 to 7. So we go 0 to 7 on each of these, and that's the opcode extensions. So if I just run this, we get some problems here. So this is actually matching things, but it thinks it needs a rex prefix. And I think that's because this operand, for example, is OXFF, and the way that I tell whether I need a rex prefix is by deciding whether something is extended, and whether an operand is extended or not is basically whether the 4th bit is set, which in this case is always true. So I need to make sure that the extended check only runs if the operand is either a register or memory. Okay. So now I'm getting the correct opcodes out, mostly. So I got B0, but for example, this one needs B1, so that's because B0 is the opcode, and then I want CX, which is index 1, so I need to OR that into the opcode in this case. So if we go down to wherever the opcode is, so here's the opcode. We'll take the opcode out, say if the form has reg in opcode, then we'll change the opcode to be, I think in this case it will be the RM variable, and we'll just use RM to get the lower 3 bits. And actually this should be ORed in. Okay, so now that's correctly like B1 here, but I'm not outputting the immediate at all. So the immediate goes after the disp. And technically the immediate can be in any of the operands, but for this right now I'll just assume that it's operand 2. So we'll say if op2 is an immediate, then we'll just switch on the width for now. So in the case of a byte, word, D word, or Q word, we do something different each time. So we'll do the bytes, we'll just append a byte from op2.value. And then these ones will have to do the little endian append. So this one is 16. This one is 32, which is fine. These need to be op2.value. Op2.value. Okay. And then this keyword one was basically if the opcode is between B8 and BF, then you're allowed to use a 64-bit immediate. So we'll say that is allowed im64 is whether the opcode is between B8 and BF. So if is allowed, then we would do a 64-bit. Otherwise, we'll do 32-bit. So 64-bit. Okay, let's see how that goes. So it looks like these ones here with the register MOV are actually instruction length optimization cases, so I'll come back to those. This is because I need to... Yeah, so I think this, some of these are probably instruction length optimizations as well, but some of them are because I haven't done the opcode extension. So opcode extension needs to be done as part of the mod RM. So I'll just do a similar thing with the reg field as I have with the RM field, which will be to say just change the reg field based on what is needed. So this will be reg field is actually reg.reg, but if the form opcode extension is valid, then the reg field will equal the opcode extension value. So let's see. I think, yeah, so some of these are still... So this one is saying want C6, but we're getting B1. Did I change the... Did I change this properly? So we got reg mem immediate C6. But we're getting B1 for that. Oh, that's because in my tests, I didn't update this to be memory access. So we'll do memory access here. Okay. So now we're just down to optimization cases. So in these cases where we've got -1 and just nothing but Fs here, this can be optimized. So we can see that, for example, this is actually a valid encoding for the exact instruction that I wrote. But if we use this C7, which is the RM destination, then this can just be sign extended from 32 bits, which means that these the upper 32 can be cut off, and we can get rid of. We can also get rid of so we can get rid of 32 of these bits basically. And in this case where the upper bits are all zeros, if you just change this to moving into an ECX instead, then the upper so the ECX with 0x7f, if you do this into a 32-bit register, then the upper 32 bits are automatically zeroed for you, which means you can get rid of the rex prefix and you can get rid of 32 bits of immediate as well. So I think this is going to be more of a form selection problem. So I'll probably want, and these are all keyword cases, so if we do the test, these are all RCX here. So if we do so if we separate out keyword, let's just separate out keyword here. So we've got keyword. So we want to say that in the case that it's an immediate 64, we definitely just want to do the B8 case. But if it is an immediate that fits within 32 bits, then we want to do this, but we want to encode the width as being dword instead. So this is where we would transform RCX into EAX, for example. So we'll put encode width here. Then I don't know, maybe this one doesn't need to be separated out, we'll see. So we'll do, so we need im64 at least, and we need imfits32, and we need to use the encode width. So if we go to emit, let's do the encode width first. So we'll say that if form.enc_width does not equal 0, then the width equals form.enc_width. So that will change the width if the form says that it should be encoded as a different width. Then I needs to do some other stuff here. So let's change this to info. Info is uint64. So we need, let's say we'll have immediate 8, 16, 32, and 64. We also need fits 32. And then we need to just do this stuff in here. So for example, we'll say that if math.min int32 is less than or equal to the immediate, and the immediate is less than or equal to math.max uint32, because I don't care about sign this here, I only care about whether the bits actually fit in this size or not. Then info or equals imfits32. And then we'll do a similar thing with a switch to say what size it is. So this one here would be 8. This one is 16. And then in the default case, we know that it's going to be 64. Okay, so that sort of works mostly. So these ones I want to do as this C7 one, the RM one, but only if it's signed. So if immediate is less than 0, then we'll say that it is immediate signed. And then this one can basically just say or signed, maybe. Okay, yeah, so Right now I'm selecting forms. It's just whichever one is the first to match, but I want it to fall through from this B8 case to this one if this one matches more flags. So I think I just need to go and implement just a very basic scoring system. So we'll have a high score here, which will be math.minInt. Then if the high score still equals math.minInt by the time minInt by the time we get here, then it means that we haven't matched anything. I'll still treat this as like the winning case in just all the time. So we'll say that high score here is math.maxInt and just break. But in this case, I don't want to do a break. High score would equal score if score is greater than high score. So I need to do some scoring here, and I think I want to do it. Yeah, I think I'll do it based on how similar the flags are. So how many overlapping flags there are, we'll add that number to the score. So we need all of the operands. So we'll say operands is equal to an array of operand. This will be op1, op2, op3, and op4. And then we'll just go over all of the operands. So we'll say for I O range over all the operands. And we want to say, we want the flags from the form as well. So we'll say, for example, the form infos or something like that will be an array of uint64. So this will be f.op1, f.op2, f.op3, and f.op4. So then we'll get the form info, which will be finfos sub I. Then we get the overlap, which is the form info ANDed with the operand info. And then we'll add that to the score. So this will be bits.ones count of the overlap. And actually this will be ones count 64 because it's a 64-bit value. Okay, so this is kind of doing it. Let's just go and check some stuff. It might be that I need to split this one out. So let's have keyword, because this one doesn't need to care about signed or not. This one needs to fit in 32 bits, but I don't know if that matters for the scoring. Okay, that works. Okay, so that's selecting all of the MOV forms, including the optimizations for instruction length. And actually, I've just realized that, if I look at the forms here, I don't care about segment registers. I don't care about memory offsets. So actually, I've just coincidentally implemented all of the form matching for all of the MOV forms that I actually care about. So maybe what I will do here is just rename this test data to MOV and operand encodings .asm, or MOV modrm SIB immediates, or something like that, just so that it's a bit more obvious what's in there. We'll get rid of these operand encoding ones. We'll regenerate this as MOV LST. Okay. Then we'll go to encoded test. So this was MOV modrm SIB immediate. Okay, that still works fine. Yeah, and so as I said earlier as well, there can actually be immediates in any of the operand slots. So if I just do a quick change here, which will be, since I've got that operands array now anyway, I may as well just range over all of the operands. And we'll just say that, for example, if the operand is not an immediate, then we will just continue. Okay, well that all seems to work. So yeah, I'll decide what to work on next, but it will probably be just a little bit more testing of immediates and then maybe moving on to some other instructions or something like that.